Good morning, Abyss. It is with my sad announcements. This will be the last day of the live feeds until September. And so we have two marvelous presentations for you. Enjoy. And then make sure you download these onto your computer. So at your convenience, when you're at Caribou Coffee by Crossroads and you see a short fat man walk in, you can say, hey, I'm watching Cool Math, the new jazz. Okay, go ahead.
Okay, so I'm Cooper Graffarkas.
And I'm Raymond Nowoski, and we decided to do our presentation on rockets.
So the reason that we chose rocketry is that both of us have been interested in rockets and how they work for many years, and we've actually done some experiments ourselves with rockets and creating very basic rocket fuels. So we wanted to explore how the math that we've learned in this class applies to some of the concepts that we're interested in rocketry. So just to give a brief history of rocketry and how it really started and developed, the first rockets were actually developed in ancient times, and these were very simple. They were used for warfare by the Chinese. It was essentially just like a little packet of solid rocket fuel, and then they were attached to basically an arrow, and it would just help the arrow go further. And then the beginning of really the rockets that use the principles that today's orbital boosters are based on, that started in 1926 when the first liquid-fueled rocket was flown, and that's this right here. An interesting thing about that is that this is actually the nozzle up here, whereas this is the fuel. So the nozzle is actually the fuel is pumped upward, which is completely opposite of how today's rockets work. And then the beginning of the space age was in 1949 when the V-2 rocket, which was developed by Nazi Germany, it was launched from American soil because we had gotten it from the Nazis after we won World War II. And then that became the first man-made object to reach space in 1949.
All right, so some basics with rockets. For the most part, any rocket that you see today, it uses the very simple principle of ejecting mass to attain velocity and thrust. Usually the exhaust is expelled as a gas. It can be accelerated out of the nozzle. Most of the time, for actually getting into orbit, it does need to use a nozzle. However, most model rockets will come in an engine that does not have a nozzle already attached to it. We can model the movement of a rocket based on the rocket equation, which we will look into a bit further in the presentation. So there are three main types of rocket engines. There is a solid state on the top, a liquid or fluid, either way, and then a hybrid on the bottom. So what a solid state rocket motor is both the fuel and the oxidizer, which are the two main components for combustion, are both solid. A liquid motor uses two different liquids. Usually it is, for the oxidizer, liquid oxygen, and occasionally in more of the new rockets, they use liquid hydrogen and liquid oxygen together for their combustion. And hybrid is basically just the oxidizer is a liquid, but the fuel itself is a solid, so they run the oxidizer through the solid particles of the fuel, and they then use that for combustion. So, what is impulse? Impulse is essentially the change in momentum of a rocket or any body moving. It's directly related to the thrust of the motor. So total impulse, therefore, is the total amount of momentum, and specific impulse is the impulse the impulse per unit of mass. And with rockets, it's especially useful because, as I had said earlier, with a rocket, you're continually losing mass.
That's specifically per unit of mass of propellant. It's not of the whole rocket, it's the unit of mass of the propellant that's burned.
All right, so calculating the total impulse and specific impulse and average thrust of a simple rocket motor. For this one, what we decided to use was a Class J model rocket. So there's different classes of rockets. I believe they're all lettered from A to...
For the smaller model rocket engines. Yeah. So this is like we talked before, this is a solid engine, so the fuel and oxidizer are mixed together. And then it's a fairly small motor. It's just like a hobbyist rocket motor that would go in like a model rocket that you would see that would just be probably a few feet tall. So then, yeah, you take the thrust curve and take it.
All right. So what we had done is we had gotten that thrust curve from just a website that had stated the specs of the motor, and we used that to determine what the total impulse was by integrating underneath the thrust curve. So we found out what the thrust per second, or the pounds in thrust per second was, which was approximately 219. The specific impulse, or the amount of time it had taken, which was about 136 seconds, and the average thrust was about 104 pounds. So that's the way that class is determined for model rockets is by the total impulse, or the max thrust. And with this one having 219 pounds per second of impulse, it is classified as a Class J. And over there we just have what the propellant weight was in the motor and the total burn time.
So then originally we wanted to like do our own model rocket, or our own model rocket motor, and then make a rig so that we could test the propellant of it. However, we couldn't really we didn't have the time to do that, and also to like create the rig is really the problem, because we've done the motors before. So we found this, and this is a real, this is a very credible source, renowned for model rocketry, and then it's like a real data, and then it also had the data that we need to get those, which is propellant weight and burn time, which is kind of hard to find. So that was nice to have. And then we just basically found the line of best fit, and then integrate that, and that gives you the total impulse. And then from that, you use those two pieces of data about the rocket to get the specific impulse and the average thrust.
And just as a comparison, this is the Merlin rocket that is currently in use on, I believe, some of SpaceX's rockets.
The Falcon 9 is the name.
The Falcon 9.
Yep.
It just kind of goes to show that you need a lot more thrust and a lot more impulse to get a rocket actually into space and orbit. Model rockets have significantly less thrust and impulse, and yeah, this is just kind of to show a real-world example of basically a souped-up model rocket.
So what's basically done here is I got some stats about this rocket engine itself, and then about the launch of the rocket. So I know that the thrust at sea level is 190,000 pounds, and then in a typical launch, the engines burn for 397 seconds. So then in this case, instead of integrating, to find the total impulse, you can just multiply the thrust by the burn time, because you already know the thrust in this case. And then that gives you, for just one engine, 75 million pound-seconds. So I believe in ours we had like 200 something for that little model rocket motor. And then and this is actually the same engine that's used on our cover slide right here. So all of these right here in clusters, those are all Merlin engines. And on this rocket, there's actually 27 of them. So on this slide, I also showed the total impulse of the entire rocket itself with the 27 engines, and that's about 2 billion pound-seconds. So that's one of the most powerful rockets that's ever been flown. Okay, so we mentioned that we were going to talk more about the rocket equation. And really what the rocket equation is a special derivation of Newton's second law, force equals mass times acceleration. So Newton's second law basically says that the greater the mass, the more force you need to accelerate it to a certain velocity, or delta V. But that only works because F equals in that equation, F equals ma. M is a constant. There's a constant mass. It's not changing. However, with a rocket, the mass is actually constantly changing, because if you think about this, it's actually working on Newton's third law, which is that when you expel something, it has an equal and opposite force. So that's how rockets work. But that means that it's constantly losing mass throughout the flight. As you can see here, this is the exhaust velocity, and then this represents the exhaust that's being lost during the flight, and that's the change in the mass, the delta M. So then the rocket equation is basically Newton's second law for rockets, so that it can be applied to a system that has a variable mass, and that is delta V, which is, as we know, the same as acceleration, and that's equal to the velocity of the exhaust times the natural log of the initial mass over the final mass. So this is basically accounting for the fact that there is a variable mass. And there's also the fact that the higher exhaust velocity of the exhaust, there's going to be more delta V, which is what you want, because you want to be able to accelerate your rocket as much as you can. So that's why we use nozzles that use the high pressure and then convert that into speed for the exhaust gases, which often go supersonic actually.
Yeah, so that's oftentimes why the main thing that people trying to launch rockets will try to optimize is that exhaust velocity, because it is the main way to achieve a higher delta V or change in velocity.
You can either have higher exhaust velocity, or you can just have more propellant, which also adds a greater initial mass to the rocket. So that's the one way that you can really increase the delta V of the rocket without giving up other things. So then, because the change in the mass is such a fundamental concept and to the rocket equation and rockets themselves, I thought that I would find a general equation for the change in mass by using the derivative of a mass function of a rocket. So basically what I did is I defined the mass at time t as equal to the initial mass of the rocket minus the exhaust of, the mass of the exhaust at time t. So this is basically just saying that you have the initial mass of the rocket, and then you subtract that from the exhaust mass that has been lost by the rocket. And then in order to find the mass that's being lost and at what rate, I just took the derivative of that, and then because the initial mass is never changing, it's a constant, that cancels out. So then you get that the change in the mass of the rocket is equal to negative of the change in the mass of the exhaust that has been expelled. And so this makes sense logically, because if you think of a rocket, this is the only way that it's losing mass. So everything else is staying the same, but it is losing the fuel. So then the change in the mass, and then it's also losing that. So then it makes sense that it's negative. And so it makes sense logically that that the rocket would be losing mass at that rate, and it would be purely dependent on the exhaust, the mass of the exhaust.
And then just a few struggles that we've had. As Cooper mentioned, we kind of had wanted to test some of our own model rockets that we've been experimenting with. We didn't, unfortunately, have time for that. Some other things, we just, with rockets, there's a lot of calculus involved. Some of it is beyond our current knowledge, and we did try and look into it.
It is rocket science.
Yeah, it is rocket science after all. But yeah, overall though, we did find a lot.
Instead of using like a smaller model rocket engine like that J class that we used, that was really nice because you have the really clear thrust curve, and then you also had the burn time exact and the exact mass of the propellant. We were going to do something more like the Merlin engine and then like do the integration for that, but unfortunately you really can't find like all of the data that you need. Like you can find the burn time often, but then finding the actual mass of the propellants is usually not given, at least for one engine. So then we had to use the smaller model rocket engine, which, I mean, it still demonstrates the concept exactly, and then we can do that comparison between the two. But that was our original plan.
Along with that, a lot of the rockets, like we had also looked at Saturn V, we wanted to maybe try and use that.
That's
since
the
it was
rocket.
Since it was such an influential rocket, we were wanting to maybe use that, and unfortunately we couldn't find any thrust curve. And the main reason we wanted that is because you'd integrate underneath it, you'd find the impulse, but realistically they don't have any instantaneous thrusts from it. When they were testing it, they just find the total impulse as opposed to actually using the thrust curve. So, yeah.
All right.